Okay, so let's continue with the ones that we didn't do last time. That's these two right here. So let's first think about the definition of the absolute value. Remember that we were talking about up at the top here. So that piecewise definition for the absolute value. If you break this up into its pieces, so I'll write it, 8 minus 2x. And we break it up into the two pieces. We have 8 minus 2x. It's going to be positive when this, the inside, is positive. So let's take the inside and make it positive. So it's going to be the inside as long as the inside was positive. So let's solve for x here by adding the 2 over to the other side, the 2x to the other side, and then divide by 2. So we get 4. So notice it says if x is less than 4. So here it's going to be 8 minus 2x if x is less than or equal to 4. And then we want to do a minus sign when x is bigger than 4. So when x is bigger than 4, we have to replace it with a minus sign. When x is less than 4, we have to leave it alone. So that's the rule here. And the way that I figured that out was by taking the inside and making sure that it was positive. So now, down here, notice that I'm coming from the right of 4. So if I'm coming from the right of 4, which of the two should I be using, the top or bottom? The bottom one, good. Yeah, so the bottom one. So here, let's go ahead and rewrite our limit, and we'll replace the 8 minus 2x with the bottom one. So that's going to be the negative 8 minus 2x over 4 minus x. And in the numerator, you can factor out a common factor of a 2. So that's what we'll do. So a minus 2, and that's going to leave me with 4 minus x. And the factors of 4 minus x will cancel. So that's what we want to do next. Those factors wipe out, and that leaves me with the final answer for our limit is negative 2. That one's pretty kind of counterintuitive. Yeah. Here, if you plug in 5 in for x in number 22, notice that if you plug in 5, the inside of the absolute value is going to be positive. So if I plug in 5, I get 15 plus 6, or 21, which is already positive. And so coming from the left and right of 21, it's still going to be positive. So you could actually just take away the absolute value bars there on this particular one. It's not on one of the edges of the piecewise function. If you write out the piecewise function, you'll see that it splits somewhere different than 5. So this is just going to be 3x plus 6 over x plus 2. So you can even take away the absolute value. And you can just go ahead and plug in 5. So if I plug in 5, there is no issue here. So we get 21 over 7, or 3. Yeah. Okay, let's do number 23. So let's go ahead and sketch a nice axis for this problem. They want us to sketch our graph here, so that's my y-axis and that's my x-axis. Let's get the easy ones out of the way. These two are the easy ones. So what we can do is we can just plot those points. So x is 3 and y is 3. So let's just plot that point right there. That's a point on the function. That takes care of this one right there. Now, the next one says f at negative 2 is 1. So we want to go to negative 2 and then up 1 right here. So that takes care of this point. Now, the remaining pieces that they gave me are limits. So those limits, I have to take individually and look at them. This one here says it's coming from the right of 3. So here's 3. and that means it's coming from the right side of 3. So they're telling me, what this limit is telling me is what happens to the function as it comes from the right side. So the function's going to be doing something. I don't know what it's going to be doing, but I do know that the y value, once it gets close to 3, the y value is getting close to 4. So what we want to do is, you can even draw a crazy function. I have no idea what it does, and I don't care, but as it gets close to 3 from the right, it should stop at 4. So the height that it stops at should be 4. Notice how my function is super crazy over here. So you could have done a not crazy function and something that's a little bit more normal, but they didn't tell me what I had to do over here. They just said that coming from the right, the y value should end at 4, is what that limit is telling me. Okay, well, coming from the left of 3, the y value ends at 2. So that's coming from the other side, so coming from 3 this way. The y value ends at 2. Notice that I put a hole here. So that hole is because the function is already defined at 3 down here. It's defined on this first one, so I had to put a hole there. I couldn't put a solid dot at 4 because the function is already assigned a value right there. And so I'm going to have to do the same thing coming from the left-hand side for this piece. So coming from the left, my function should end at 2, so I'm going to put another hole there. And you can make something crazy happen in the middle, but I'm going to stop short because I think this next limit might tell me what I need to do for the rest of it. Let's check. The limit says as x goes to -2, so -2 is right here on the x-axis. So we're talking about coming from the left and from the right. Notice that this is a two-sided limit. They don't have a plus or minus up there. So a two-sided limit means that I'm coming from both sides. So both sides have to end at the same y value, and that y value is 2. Is what they say. So let's go here at -2. There's already a value assigned, so I'm going to go up to 2, and I'm going to put a hole there. Because it's already assigned a value at 2, I can't define it again. So now, coming from the left, the function might do something crazy. Who knows what it does, but it might look something like that. And then coming from the right, it's got to connect to that right there. So I'll just go ahead and connect those two functions up, something like that. So yours could look a little different than mine. Yours might not be as crazy and wavy, but that's okay. I just did that to make a point that it doesn't really matter. The only ones that they specified, these limits, really, I took care of those, what they specified. But yeah, good. Any questions on that before we go to the next section here? Okay, well this is today's notes. We're talking about limits at infinity. So this is a little different. It's kind of a different scenario than our previous section. Our previous section we were dealing with that NAG acronym. We just tried to plug in first. And this time, if I try to plug in a number, like in our first example, if I try to plug in a number, I'll get 4 plus 5 is 9 over 0. So anytime you get a 0 in the denominator, your answer in your limit, in a number in the numerator. So we have a number in the numerator that's non-zero, and a 0 in the denominator. That means that my answer is going to be one of 3 things. It's either going to be infinity, minus infinity, or D and E. So that's one of the 3 things. So I almost like these limits at infinity because they're a little bit easier to answer sometimes. They still require a little bit of work, but they're what we call analytical. The work has to be done in your head. So let's look at the work. So what's the work here? So we have to, how do we decide which one to give it? Infinity, minus infinity, or D and E? Well, you want to test the limit a little bit from the right and a little bit from the left. So in your mind, so I'm going to draw a little thought bubble. This is something that should be happening in your mind. I want to plug in a number like 2.1. That's coming from the right. And a number that's a little less than 2, like maybe 1.9. So that's from the left. So let's plug in a couple numbers, something like that. So in the numerator, if I plug in 2.1 times 2, that's going to be about 4 plus 5 is 9. That's positive. So the numerator is positive. What about the denominator? Is it going to be positive or negative if I plug in 2.1? Positive. So this is going to be positive. So that means coming from the right, the limit goes to infinity. So what I'm going to write over here is the limit as x goes to 2 from the right of 2x plus 5 over x minus 2 is positive infinity. Now we want to check coming the other direction. Hi. Oh, your lunch. Yeah, right here.
Oh, no, no.
Oh, your phone. Can everyone check in their desk to see if there's a phone in there? No phones? No? Okay, maybe another room. Sure. So now we want to write the limit coming from the right, or the left, of the same thing. So we're checking the left and right. And now this one we're plugging in 1.9. So if I plug in 1.9 in the numerator, that's going to be a little bit less than 9 because this is a little bit less than 4 plus 5 is a little bit less than 9. So this is going to be positive over, is this going to be positive or negative if I plug in 1.9? Negative. 1.9 minus 2 is a little bit negative. So this is going to be negative infinity. Notice that these two one-sided limits don't match. So that means that our answer has to be D and E for number 1 here. So this is D and E, and the reason is because the two one-sided limits don't meet up or match. Now, it's important to note that because we are writing infinity here, it doesn't mean that the limit actually exists. The limit still doesn't exist. It's like being a little bit more specific. It's like, hey, the limit doesn't exist, but it's going to infinity. It's like kind of telling the reader what's happening. Infinity is not a real number, so it's not like it's actually going to some number. But yeah, let's try number 2. So again, we want to plug in numbers that are a little bit less than 0 and a little bit bigger than 0. So in my thought bubble here, I'm going to think about numbers like 0.001 and negative 0.001. So this is on the right and that's on the left of 0. Those are the numbers that I'm plugging in. Typically, you don't even write those on your paper. You just think about them. These are analytical limits. So the limit as x goes to 0 from the right of 4 over x squared, and the limit as x goes to 0 from the left of 4 over x squared. So we want to check out the two one-sided limits to see what we get. Now coming from the right, we know it's going to be infinity or positive or negative infinity, one of the two. If you look back at the original, notice that we get 4 over 0 if you try to plug it in. So we know that it's going to be one of these three. So here, what we need to decide is just whether it's positive or negative. So if I plug in a number a little bit bigger than 0 in for x and square it, is that going to be positive or negative? Positive. So this is positive infinity. What about a number a little less than 0, like negative 0.001, and plug it into x squared here? Is that going to be positive or negative? That's also positive. They're both positive. So that means that we get a positive infinity for that one. So again, it doesn't mean that the limit exists, but it's being a little bit more specific. The graph looks something like this. The graph is going up to infinity on both sides of 0, and both sides are kind of approaching 0 together, or excuse me, infinity together. Yeah. Okay. Well, let's go ahead and read this next bit here. The limit as x goes to infinity. And the limit as x goes to negative infinity. These are talking about the end behavior of the function. So what's happening to y as the x values get very, very large. And so here in this little blank space, we're just going to draw a few different graphs to explain like what possibly could happen. So there are a few different cases. So here, a first case, maybe the graph does something like this. So maybe the graph goes to infinity. So maybe as x goes to infinity, maybe y goes to infinity. So as this goes up, that's one possibility. So as x gets big, y gets big. It's also possible that the graph could go down, something like that. So as x gets big, y gets big negative, so it goes down. And another case that we might see is if maybe we have a graph that approaches some value. So as x gets big to infinity, y goes to some value L, some limit value. We would call that a horizontal asymptote. So those are really the main cases. There are some other special cases. For example, the graph might not even exist. There might be no graph. The function might not even be defined. Also, you could have some strange oscillating things between infinities. So there's some weird cases, but these are the three main ones that we'll probably see. And I mentioned a horizontal asymptote. So how do we decide which one of those for rational functions? So here we're looking at only rational functions, and you might remember this from pre-calculus last year, but when you're taking a limit as x goes to, notice each one of these are going to infinity, each one of our limits, what you want to do is look at the exponents, the powers, and compare the powers to see how fast they're going. And the rule is, if the powers are the same, you look at the coefficients, that's the limit. If the powers, the largest power is in the denominator, it goes to 0. And if the largest power is in the numerator, it's either going to go to plus or minus infinity. So let's have a look at each one. So the first one here, this one, we notice that the powers are the same, so we're just going to write 4 over 3. You look at the coefficients, 4/3. That's the limit as x goes to infinity, since the powers matched. The next one here, since the largest power is in the denominator, we want that power to grow, that one grows quicker, so the denominator is getting bigger quicker, that's going to 0. Anytime you have a number over something very big, this is going, you could say going to 0. It's pretty much 0. The fraction, the denominator, decides how many pieces you're cutting the numerator into. So if you cut the numerator into infinitely large pieces, then that means that you're getting infinitely smaller pieces. They're going to 0. Okay, and number 3, let's look at that one. The numerator is the largest, and so now we have to look at the coefficients to see is it positive or negative. And it looks like as x is growing, the numerator and denominator will both be positive, which means that this limit is going to positive infinity. It's going to look like this first picture right here. So if the 4 in front of that x cubed were negative, then that's actually going to decide the direction. It's going to go down. Or if that 3 were negative, it would go down to negative infinity. It decides the sign, the direction of it. Yeah, so again, the rule, I don't think I'll write out the rules, but the rule is if they're the same, the coefficients match, or the powers match, you take the coefficients. If the denominator is largest, it goes to 0. Or the denominator is largest, goes to 0. If the numerator is largest, it goes to plus or minus infinity. Okay, cool. So that's what this box is here that I should fill out. So if the largest power is in the denominator, it goes to 0. The largest power is in the variable in the numerator. That's going to go to plus infinity or minus infinity. And if the denominator and the numerator have the same highest power, then it's going to be a over b, where we'll say where a and b are the coefficients of the highest power terms. in numerator and denominator, respectively. Denom. Okay. So A is the highest power, or the coefficient of the numerator, and B is the coefficient of the denominator. All right. So now that we know the rule, let's just go kind of hog wild and answer these. So here, notice all of these limits are as x approaches infinity or negative infinity. So you have to be careful when it's going to negative infinity that you watch out for that sign in the second case here, because you might be going to positive or negative infinity. But for number 1 here, the largest power is in the denominator, so number 1 goes to 0. Good. Number 2, the coefficient or the largest powers are the same, so we want to look at the coefficients. So the limit is 4/3. Very good. Number 3, the limit's going to infinity. The largest power is in the numerator, so the numerator is growing big positive. The denominator is growing positive, but the numerator is bigger, so this is going to positive infinity. So you just look at the sign to try to determine whether or not it's positive or negative. Okay, so here, number 4, if we plug in, let's see, with the highest powers in the numerator, so again, the numerator is growing quicker, so this is going to plus or minus infinity. Notice that the coefficient is negative, so negative 2 there, so this is actually going to go to a negative infinity. So the numerator is growing really big negative, while the denominator is growing big positive, but not big enough quick enough. Number 5, again, the numerator is the largest power, and the denominator is also an even power. Notice that they're both even powers, and as x goes to negative infinity, so that means I'm plugging in a large negative number, is the numerator going to be positive or negative? It's going to be positive even though I'm plugging in a negative number because of the even power. Same thing with the denominator. Even though I'm plugging in a negative number for x, the denominator is going to be positive because we're squaring that negative number. So even though I'm going to negative infinity for x, the limit in this case is going to positive infinity. Yeah. Okay, number 6, let's have a look here. This one's a little different. Notice here that we have the square root of x squared in the numerator. Now the square root of x squared is actually equal to the absolute value of x. They're the same thing. So this has the same magnitude or the same rate of speed. It grows the same quickness as x. So these, we actually have similar powers, even though it doesn't look like they have similar powers because that's x squared. Since we're square rooting it, it's bringing them back down to the same level. So we're actually looking at the third case here, where the powers match, even though it looks like it's an x squared. We have a square root over it. So since the powers match, you have to take the coefficient. The coefficient of the numerator is the square root of 1, so I'm square rooting the coefficient in the numerator. And the coefficient of the denominator is 2. So it's the square root of 1 over 2, or just 1/2 is what the limit in this case will be. What would it be going the other direction, just out of curiosity? What if I took the limit as x goes to negative infinity? Would the numerator be positive or negative? Well, we're squaring it, right? We're squaring it. So once we square a negative number, it's going to be positive, and then you square root that. So it's going to end up being positive in the end. In the denominator, is it going to be positive or negative? Negative, so it would be positive over negative. So in the case of going to negative infinity, it's actually going to go to negative 1/2. So they have two different limits depending on which way you're going, whether it's positive or negative infinity. So number 7, do the powers match here? Are they comparable? Yes, it's like number 6. They are comparable. The limit is going to negative infinity this time, so the numerator is a positive. Square root of 1 is the coefficient. I'm square rooting the coefficient of x squared. And in the denominator, this is a 2x. So notice we're going to negative infinity. So that x in the denominator is actually going to be negative. So we want to put a negative 2 there because of the direction of x. So this is actually going to negative 1/2. Oh, that is the exact opposite of, that's the one that I was referring to. I didn't know that I put it up there. Okay, well, let's try number 8. So this one, the powers are comparable again because the square root of x squared. So we want to square root the coefficient of the numerator and the denominator's coefficient. There we go. So square root of 2 over 3. All right, good. Okay, well, number 9, let's have a look at this one. So the limit as x goes to infinity of e to the x. So these say use graphs to determine the following limits. So we want to think about what e to the x looks like. So I'm going to do a small sketch of e to the x next to this problem. So let's go ahead and put that right here. So e to the x looks something like this. Crosses at 1. The y-intercept is 1. And so as x gets really big, what happens to the y values? As x gets big, y values get big as well. So that means they're going to infinity. It's going to infinity. I really like number 10 because you have to think back to what the inverse tangent actually looks like. It's been a little bit of time since we've seen that. But the inverse tangent looks something like this. So pi over 4 and negative pi over 4. The limit is going to have the graph go something like this. So we have asymptotes horizontal going like this. So it's like tangent, except one period of tangent flipped on its side is really what inverse tangent looks like. Okay, so if I have x going to infinity, what would the y values get close to? Whoops, I have pi by 4. These are pi by 2s. I'm sorry, those are pi by 2s. Pi by 2s. So as x gets large to infinity, the y value should get closer to pi over 2. So these get closer and closer to pi over 2. So you really have to know the graph of inverse tangent in order to answer a question like that. There's no other way. It's not like you can just plug in infinity into inverse tangent and see what happens. You can't. So really the only way to understand that question is to graphically kind of think about it. This one, so we can answer number 11 since we just answered number 10. It's going the opposite direction. So this one's going to be a negative pi by 2. Negative pi by 2. Number 12 involves a special technique and a theorem called the squeeze theorem, or when I was taught it, my instructor called it the sandwich theorem, I think, something like that. But this is the idea. Let's see. We'll try to put this somewhere, maybe up here. The largest that cosine is ever going to be, what is the largest that cosine is ever going to be? Is 1. That's the biggest cosine is ever going to be. So I'm going to say this is less than or equal to 1 over x. And this, what's the smallest cosine is ever going to be? Negative 1. So this this function is actually bouncing back and forth between x over negative x over 1, 1 over x, and 1 over x. And so if I come through here, this is what the squeeze theorem does. If I come through here and take a limit as x goes to infinity on each one of these, Uh, what will the limits on the end be? What's this going to? 0, the largest power is in the denominator. Over here, the largest power is in the denominator, so it goes to 0. So what the squeeze theorem is telling us, we've squeezed this function right in between two functions that we know. And they both go to 0. So if you're in between 0, you've got to be 0. So this limit by the squeeze theorem is 0. The denominator is growing big, quick. These next couple ones take a little bit of doing, so I think we might actually continue these once we return from lunch. So I think I'll go ahead and dismiss you guys for lunch, and then we'll pick up right here when we left off. Excuse me. Okay, so let's go ahead and pick up with 13 here. So this one's a little bit more difficult. If you try to plug in Infinity, if you think about plugging in Infinity, you'll notice here that this is going to be positive infinity, this first one, and then you're subtracting another infinity. So it's like infinity minus infinity. So what do you do here? So this is kind of a challenging limit. So what we want to do is actually multiply by 1, but we're going to choose it in a special way. We're going to multiply by the conjugate on the top and bottom. So let's go ahead and put a fraction bar here, and then I'm just going to multiply by the square root of x squared plus 1 minus x, and that's going to be a plus x if we're doing the conjugate. And then you also want to put in that in the denominator, so x squared plus 1 plus x. Typically, I don't show the process of distributing that or foiling that numerator with the conjugate. I just write out the product. So the first term multiplied to each other, that's just going to be x squared plus 1. The square root disappears off of it. The cross terms are going to cancel. The square root of x squared plus 1 times x, and then the minus x. Those two will cancel, so I don't even write those. And then the minus x times x is going to be a minus x squared. Now the denominator is going to still be the x squared plus 1 plus x. Now, the beauty of the conjugate is that the numerator there is going to simplify so much. So it's simplified quite a bit. And now we can just reduce that x squared term. And then let's go ahead and rewrite. So this is the limit as x goes to infinity of just 1 over the square root of x squared plus 1 plus x. Now, it seems like infinity minus infinity, it seems like the two infinities would just cancel or something like that. Sometimes it does. In this case, it looks like as x grows in the denominator, we're adding infinite plus infinite down here. These two are going to positive infinity. And so the denominator is growing larger and larger quick. So this whole fraction should go to 0 is what this one is going to. Yeah, good. Number 14 is very similar. It's just an uglier conjugate. So let's actually switch colors and do this one. So you just want to multiply by the conjugate. This minus sign is going to become a plus. So we have a square root of x squared plus x plus 1 plus the square root of x squared minus x. And that's also going to go in the denominator. So let's put that same term, x squared plus x plus 1, and then a plus square root of x squared minus x. Okay, there we go. And again, when I distribute that conjugate out, I typically don't show all of the work just because it's a lot of terms to write out. So I'm just going to show the terms here, the first two terms. So the first term, the square root is going to disappear. And then the cross terms are going to cancel, and then I'm going to be left with the product of the last two. So the middle and the last one there. So if I multiply those, that's going to be x squared minus x. Notice I put parentheses around them. You have to have those parentheses there. So let's put the denominator back in there. The square root of x squared plus x plus 1, and then a plus square root of x squared minus x. There we go. That's our denominator. And Let's see, do I get any cancellation in the numerator? It looks like I'm going to have a couple things canceling. Maybe the x squared. So this x squared is going to cancel with those. And let's simplify and rewrite here. I think I'm going to kind of continue on the next line here. Let's say limit as x goes to infinity of what's left over in the numerator. I'm going to have two x's, and then you said a plus 1, plus 1. That's right. Yep. And then our denominator is the same. So x squared plus x plus 1, and then plus the square root of x squared minus x. Now this one's a strange one. So now when I'm looking at these, the powers, notice they're comparable again. The power in the numerator is x to the first, and the square root of x squared is still a comparable power of this fraction. So they still have x to the first kind of comparable power. So what we want to do is look at the coefficients of each one of them. So the coefficient in the numerator is 2, and the coefficients in the denominator here, if you just want to skip straight to the answer, you could show some fancy algebra here to jump to this conclusion. But I think this is perhaps the easiest way. So what I'm doing is I'm looking at the coefficient of my x squared terms down there. And as x grows, as x gets larger and larger, this is going to be getting closer and closer to the square root of 1, and this is going to be getting closer and closer to the square root of 1 as well. So our final limit here is 2 over 2, which ends up being 1. So in this case, we have an infinite minus infinite, and those end up kind of balancing out at 1 instead of 0. It's kind of strange. Those are difficult limits, not very easy and not common. Pretty difficult. Let's move on to the next page here. So here we're given two piecewise functions. I can sketch them real quick. I'll sketch them individually. So here we're at 3, 1, 2, 3, and 1, 2, 3. F looks like, when x is less than 3, it looks like 2. So it looks like this, all the way up to 3. And we'll put a hole there because at 3 it's not defined. And then when x is bigger than 3, it looks like 4. So this is F. Now G, if I plot that, when x is bigger than 3, it looks like 2. And when x is less than 3, it looks like 4. It's like they're the opposite of each other. Now, I think you would agree that both of these functions are broken at 3. There's a jump in the function. And the limit would not exist at that point. The two sides don't meet up. But what if I add the functions together? So notice they say find the limit as x goes to 3 of f of x plus g of x. So let's rewrite that down here. So of f of x plus g of x. Now, remember what I said earlier about trying to distribute the limit? I said this on your homework. You can see here on the board how we distributed the limit across a product. Here, you can distribute limits across sums and products provided that the limits exist. Remember how I put that little caveat in there? So here, do the limits exist of these individual functions at 3? No, they don't. The individual limits they don't exist. So now, in order to consider this, I have to do two one-sided limits. So I have to look at the limit as x goes to 3 from the left of f plus g, and the limit as x goes to 3 from the right of f plus g. Now I'm viewing f plus g as a whole function together. They're joined. So I'm kind of putting them together. I can't distribute the limit over each one of them because the individual limits don't exist. But f coming from the left of 3 looks like 2. So this is going to be the limit as x goes to 3 from the left of 2, and g looks like, coming from the left, looks like 4. So the limit coming from the left of f plus g is 6. Now coming from the right of 3, that's coming from this direction. F looks like 4 and g looks like 2, so it's going to be 4 plus 2, or 6. So coming from the left and right, the answer for this limit is 6. So the two-sided limit actually does exist, even though both of these individual functions, f and g, are broken at 3. It's almost like they perfectly complement each other. It's like they fix each other. The functions are broken, but they fix one another. It's a very strange kind of limit. But here's another one, example 16. It's very similar to what we just did, except the function's a little different. I'm not going to sketch these, but the principle is exactly the same. So each one of these functions are broken in some way, and so what we want to do is we want to consider the one-sided limits. So let's consider the limit as x goes to 2 from the left of f plus g, and the limit as x goes to 2 from the right of f plus g. So I'm looking at the individual one-sided limits, and this time I'm going to have to replace f coming from 2 from the left. F is going to be less than 2. It's going to be 2x plus 1. So here we want the limit as x goes to 2 from the left of 2x plus 1. This is f. That's what f looks like when it's less than 2. And what does g look like when it's less than 2? It's going to be 5x minus 8, so 5x minus 8. And now we can actually simplify this and evaluate the limit. So this is going to be the limit as x goes to 2 from the left is going to be 7x minus 7. Is that right? So 14 minus 7 is 7. Yeah, okay. And now let's try the next one coming from the other direction. So this one's limit as x goes to 2 from the right. And here, coming from the right, f is 3x minus 4. And coming from the right of 2, g is 4x minus 3. So this is 4x minus 3. And now let's simplify that and evaluate. So that's going to be 7x minus 7. And plug in 2, you get 7 again. So both of these, even though each of those individual functions, if you try to plug in 2 into the top function here, I'm going to get 5. If you plug in 2 in the bottom function here, I'll get 6 minus 4 is 2. So 5 and 2 certainly don't meet up. So this function f is broken at 2, and so is g. They're both broken. But when you add them together, it's like they perfectly complement each other. They connect each other. They kind of fix the problem. Yeah. But the key here is you can't distribute the limit over the sum. It's tempting to want to and to try, but you can't. This one is kind of the similar idea. These are the greatest integer functions. So the greatest integer functions, if you remember, if you're the greatest integer that you've achieved, so the greatest integer of 2.5, the biggest integer that you've achieved is 2. So that would be 2. And so so here, the greatest integer function looks like you might have called it step function in algebra or in precalculus. And that step function is defined on the right and whole on the left. So that's what the greatest integer function looks like. And so it's obviously broken in a lot of different places. And if I take the limit, say at 3, so here is 1, 2, 3, we'll see that coming from the left, the value of the greatest integer is at 2. Let's see, 1, the greatest integer, whoops, I've drawn my axes a little bit off. There we go. this is 2, and this is 3. So the greatest integer here at 3 is 2, and then if I go one higher, that's up at 3. So coming from the left, the greatest integer is 2, and coming from the right, the greatest integer is 3. So the point is that the limit doesn't exist at 3 for either one of these. But if I take the limit and replace each of those functions, f and g, in there. So coming from the left of 3, that's like 2.9. The greatest integer is 2. 2 minus 2 is 0. And coming, so I guess we could put coming from the left here. So this is going to be 2 minus 2 is 0. And then coming from the right, this is going to be 3.1, which is 4, and 3.1, or excuse me, 3, and 3.1, which is 3. So 3 minus 3 is 0. So in this case, or you could just view it as these are going to return the same value at every single point, so they're always going to cancel each other. Even though the limit doesn't exist on either one of these functions, their difference is always going to be 0. So the limit is 0 for that one at 3. I don't know, is a function f given for this one? Given the function, I don't know that we're going to be able to do that one there. I think I remember that was broken last year. I could, is that the same function as, I think this one's the same as number 16. So this is the same as 16. I should have removed that off of our notes packet. But okay, so I haven't checked your homework yet, so if you would get that homework out, and I'll come around and check that. I think that's it. That is the last page for our section. Next week, when you see me on Tuesday, I'll continue with continuity. So go ahead and get that homework.